Hello, everybody, and welcome to the very first scientific biography video, where we're going to take a look at different scientists who have done important things throughout history and contributed to our knowledge of the world. We're going to start off with someone that everybody should probably know about, at least a little bit already, but we're going to go a little bit more into detail, and we're talking about Albert Einstein. If you don't know who Albert Einstein was, well, you'll definitely know him by the end of this video. Albert Einstein was a German-born physicist, and his work is known for its influence on the philosophy of science, as well as other things, but he definitely contributed in that department as well. He received the Nobel Prize in Physics in 1921, and he lived in Switzerland in the United States after he lived in Germany. During World War II, he leaves Europe and comes to the United States, and he ends up requesting that President Roosevelt investigate the potential of nuclear weapons because he knew that the Germans were working on it. And he ended up dying in 1955 at 76. Einstein was known to struggle in school, and there's a lot of people who think that he may have been on the autism spectrum, at least a little bit. He also received his academic teaching diploma from the Swiss Polytechnic School in Zurich in 1900, so he was a teacher. And then he received his PhD from the University of Zurich in 1905. Let's talk a little bit about his scientific achievements, what he was able to accomplish as a scientist. The first thing is his theory of general relativity. Now, first of all, I'd like to remind you that a theory in science is not the way that we use it colloquially. A theory in science means that it's heavily tested and there's data to support it. So that means that it's not just a theory of general relativity. It's something that actually exists. We have proof that this happens. Okay. General relativity is just the geometric theory of gravity. It's basically how we describe how gravity works. And it's a lot more complex than just the apple falling from the tree. There's a lot more to it, and that's what Einstein came up with. He really applied that smaller version of gravity that Newton came up with that exists on Earth, and applied it more to a gravitate or to a universal scale. And this model shows that the curvature of space-time is directly related to the energy and momentum of matter and radiation present. So the larger the object in space, right, the more space-time will be curved around that object. And he did all the things to kind of do that. And so he was really able to do this, and it really changes the predictions of some of the concepts that would be based on classical physics. So what we thought we knew about it wasn't exactly the case. Let's go to the next one. His next one, special relativity. Now, special relativity is kind of like a very specific thing about space and time, and it's based on two postulates. One, the laws of physics are invariant in all inertial frames of reference. So basically what it means is that physics, the laws, even I don't really completely understand special relativity. It's really complex. I do know someone who would be able to explain it much better than me, but I do know it's important. And the other thing is the speed of light in a vacuum is the same for all observers, regardless of the motion of the light or the source of the observer, which basically means that the speed of light is kind of like the universal speed limit. Nothing can go faster than light can. And so special relativity really kind of had big influences on things like the Doppler effect, relativistic mass, that speed limit I talked about, mass and energy being equivalent, and how time dilates as you go faster or slower. His other most maybe famous thing that he's known for is the equation E equals mc squared. It's the thing you're going to see on all of, like, the posters with Einstein, stuff like that. And really what it's saying is that there's a relationship between mass and energy. See, the E here is energy, and that's equal to mass times the speed of light squared. So basically it implies that a really small amount of mass corresponds to a massive amount of energy. So that's kind of where his idea of a nuclear weapon kind of came from, right? This really small mass, if it's going fast enough, like an atom can, it can correspond to this huge amount of energy. And so that's why that kind of thing was able to come about, because he was able to derive this equation. So that's really Einstein's work right there. The photoelectric effect is the emission of electrons when electromagnetic radiation hits a material. So basically, if there's like some kind of light or radiation hitting stuff, electrons are going to get knocked off of it, and that's called a photoelectron when that happens. So it's an electron that's been knocked off by radiation. The photoelectric effect was important because it really disagreed with a lot of classical ideas about electromagnetism, and it shows more proof that quantum physics is different from classical physics. Right? This is whole separate branch of things because we're talking about really small things instead of bigger general stuff. Another really big thing that he was able to kind of talk about are gravitational waves. And gravitational waves are disturbances in space-time generated by an accelerated mass. And these disturbances propagate as waves outward from the source at the speed of light. Now, back all the way when he was working on this sort of stuff, that he had no proof that this was actually a thing. He just thought it would happen based on his other research. So Einstein was basically like, well, if this happens, then this must happen too. And people were like, yeah, okay, Albert, whatever. But really, these gravitational waves can carry energy, and it's very similar to electromagnetic radiation, right? More quantum level science. And the first direct observation of a gravitational wave happened in 2015. So some 60 years after Einstein passed away, we were finally able to observe a gravitational wave. And we were able to do that. We saw the merger of two black holes due to our LIGO gravitational detectors in Livingston and Hanford. So basically, we set up these special detectors in places to see if we could actually detect this stuff, and we were able to. So that's really cool. Way to go, Einstein, on that one. The other thing Einstein looked into is a wormhole, and he collaborated with Nathan Rosen on that. The wormhole that Einstein and Rosen modeled are just connections between areas of space that can be modeled as a vacuum solution using his field equations that he came up with. These kind of wormholes, though, were later proven untraversable, so they can't actually happen. So he thought they could. Turns out, because of some other factors, they don't really work that way. One of the major things he also came up with is called wave particle duality. And this is something that we've kind of moved on from a little bit in physics, but it's still kind of a big point of it. And it's the idea um, that waves, light can travel as a wave or as a particle. And this means that energy quanta act in some respects like an individual point, but they also act like waves too, and so they're different. So he really kind of created the concept of a photon, and we've kind of expanded on that more since then. So now it's not as well. It's never really been simple, but it's been expanded on since he worked on it. And now one of the final things that he really contributed to is called unified field theory. And unified field theory is kind of the first attempt by physicists to unify all the different branches of physics into one theory in the quantum era. And so Einstein came up with this unified field theory when he attempted to unify general relativity and electromagnetism. So he was trying to smish two things that aren't necessarily connected together into one unified theory. And now unified field theory is kind of great because it's got these lofty goals of what we can do with physics. And nowadays they're still working on that. It's not called unified field theory anymore, but they're still trying to come up with the one thing that describes all phenomena in the universe. So this is kind of a good step in that direction that Einstein took, pushing us towards that goal of having one theory that describes everything. Thank you so much for watching. Thank you for learning about Albert Einstein a little bit. We'll be having more, obviously, scientific biographies coming up in the future. If there's somebody that you think should be in a scientific biography video, go ahead and comment their name in the description. Or in the comments. I do read those. So if you comment, I will see it and I will put it into my list. We can get it done. So thank you so much. I hope you've enjoyed it, and we'll see you next time for some more science biographies. Bye. Oops, I hit the wrong button.